Hello and good afternoon, everybody. Welcome to already fifth episode of our webinar series on R&D activities on sCO2 in Europe by ETN Global. My name is Jitka Spolcova and I will talk you through this session. I work as a project officer for ETN Global, which is an international membership association that represents the entire gas turbine value chain. If you remember, in the last few episodes, we spoke about component challenge. Today we will continue, but today we will close this chapter by presenting expanders. As always, I would like to let you know that this webinar is in cooperation with 9 European R&D projects whose logo you can see on the screen. Once you receive this presentation, you can click on these logos and you will get more information about each of those projects. For a good webinar experience for all of us, I have to tell you a few quite unentertaining subjects. I have to let you know that this webinar is recorded. Second thing is, I would like to ask you to mute your microphones and switch off your cameras unless you speak. The third topic is very important, questions. So you have basically two options. You can either keep your question till the end for a Q&A session, or if you like, you can already during the session start typing your question in the chat. All the questions will be answered either during the session. This is valid for majority of questions. If there are some very difficult ones or if there's too many of them, we'll make sure that we will answer them after the session. You will need your phones because we'll have a few Slido questions. And unless you really want to, you don't need to take many notes or screenshots because after the webinar, as part of proceedings, you will receive all the presentations and also the access to the recording of the session. So who are the key people today? As you probably know, because we share this information, we will have 4 speakers today as opposed to 3, which we had in the previous sessions about components challenges. So we have Alberto Traverso, he's from the field of academia, and then we have 3 industrial speakers. We have Markus Sauerborn from Atlas Copco, we have Stefan Glos from Siemens Energy, and we have Andrea Paggini from Baker Hughes. As you can see, you are definitely in good hands. We are very close to being done with the introduction, and I'm sure that you want to see the presentations and all the speakers. But before we do it, I'll ask you to take your phones because this is the moment for the first Slido question. I think that the answers are quite settled. So if I can ask my colleague Stefan, can you please help me debriefing the answers? Is it something that you expected or are you rather surprised about the answers?
No, I say so. I see here DGS seals and sealing and dry gas seals. So this is all related to one. So I would, if I take these together, I would say most of the answers are related to this sealing aspect, and there I would say yes, that's in fact one of the largest challenge. The temperature, I would say it really depends on the use case. Yeah, but in general, yes, I would agree to that. The thermal management, I'm not really sure what's behind that, to be honest.
Yeah, maybe we can keep this for later on for questions.
Yeah.
I guess that also many topics that are written on the screen will be covered in our presentations. If not, then there is obviously the time to ask questions. Okay, very well. So thank you very much for your interesting answers and for the briefing. So we are totally ready for the first speaker. So while Alberto is getting ready with his presentation, I have the pleasure to introduce him to you. So Alberto Traverso is a full professor of energy and environmental systems for mechanical engineering at the University of Genoa in Italy. He's also adjunct professor at West Virginia University in the US and research scholar at National Energy Technology Laboratory in the same country. He published more than 200 scientific papers, 11 invited lectures, and 17 patents. And what's very interesting is that he's also founder of 2 startup companies. One is called Blue Energy Revolution, and the other one is SIP Technologies. So this is all from myself for the moment. Alberto, the floor is yours.
Thank you, Jitka, for your kind introduction. Ladies and gentlemen, welcome to this webinar. My speech works as an introductory speech where I would like to discuss and review together with you which are the boundary conditions that we find in the main relevant applications and demonstrators for supercritical CO2 turbines. And so to set, let's say, the stage for the next presenters that actually will talk about the specific technological solutions. So I would like to really briefly review with you that are expert, most of you, of the supercritical CO2 application panorama. And then I would like to have a look at the boundary conditions set for turbines in concentrated solar power plants, for those that are targeting waste heat recovery plants, and those also for nuclear power plants, which is actually somehow an original application that was thought for supercritical cycles. I'd like to mention one outlier turbine for sake of completeness, and then also look at future for turbines that potentially are being used for energy storage application. Finally, I also would like to talk about the 2-phase flow supercritical CO2 nozzles that are basically those that are currently in the market for the refrigeration cycles, and some summary conclusions with you. So within the panorama of supercritical CO2 applications, I'm going to focus today only on a few of them: concentrated solar power, nuclear, and waste heat recovery. But also, as I said before, touching on energy storage, as well as when I said 2-phase flow that is occurring in CO2 refrigeration cycles, which is quite different from the power production one, but still is supercritical CO2 cycles.
Alberto, we cannot hear you. Something happened and you are muted.
Oh, okay, someone muted me. You can hear it now. Okay, so the STEP project is probably the most prominent one, and is targeting a 10 megawatt net power, but the turbine is actually 16 megawatt. And this comes from the Sunshot program targeting CSP application. And in this case, if we look at the turbine itself, we find some features that are common also to other turbines, which has a quite, let's say, a cylindrical shape of the whole shaft. And this poses challenges in terms of thermal management. This was one of the questions of the audience: thermal management of the hub itself, as well as about ventilation losses that may occur due to the too small, let's say, size of the blades. In terms of boundary conditions, we have quite a challenging inlet temperature, more than 700 degrees C in this case, and a typical supercritical pressure up to 250 bar at inlet, but also the 92 bar at the outlet, which is not negligible, because this means that in the cycle you have to deal with minimum pressure, which are in the supercritical region, and at least are 85 or 90 bar. If we go ahead and we look at a companion project similar, but being carried out in Europe, this is the Solar School project, where an expander will be developed and integrated into a supercritical recuperated cycle, simply recuperated, and will be operated in Portugal. And this machine actually is sized for 2 megawatt gross power. The overall system targets to more than 1 megawatt net power. And in this case, we can find a little milder boundary conditions. In particular, we see less than 200 bar inlet pressure, which is 185, and 665 degrees C, which is a little bit exceeding the conventional limit for steam turbines. So in this case, still, the demonstrator will be carried out in Europe at lower size and will represent an important benchmark for the industry. If instead of CSP plant, we go to projects that actually are targeting a different perspective, so waste heat recovery, we see that the boundary condition for the expander goes to, let's say, less demanding conditions. And in particular, if we mention, for instance, the cooling project, we see here that from the public simulation published by them, there are transient, significant transient in inlet temperature, but more or less it's always below 400 degrees C. So the plant in this case is still handling a pressure in the supercritical region, but the temperature are much milder. This means that for the turbine, low-grade steel material can be used. I also picked up a nice nuclear application that was performed in Europe. It is good to mention before describing this that the STEP project is also being evolving towards nuclear application in the United States, but in that case the target is really as the main power producer unit of a nuclear power station. In this European project, it had a different target. The idea was to develop a prototype for emergency cooling of reactors of nuclear power plants, so that to potentially delay or eliminate the need for human intervention, even for 3 days, in case of accidents such as station blackouts. So in this case, the primary circuit of the nuclear power station serves as a heater for the supercritical CO2 cycle, which has the main objective just to cool down the primary circuit. And so we can see that the boundary condition, the pressure is not reported, but it's quite similar to the previous one. So we say below 200 bar, but that range. But in this case, the temperature is quite low. So we see a TIT of about 200 degrees C. I said I wanted to mention outlier turbine. This is the only oxy combustion case I mentioned, but for this cycle, also called as a net power cycle or alarm cycle, the conditions to operate the turbine are particularly demanding. In fact, the system targets power production from fossil fuel with parallel CO2 separation and export at pressure to some reservoir. And in this case, we see that the design condition for the turbine is 300 bar with a pressure ratio, with expansion ratio of about 10. And this is quite large compared to the other closed loop supercritical CO2 cycles. In the other cases, the expansion ratio was in the order of from 2 to 3, depending on the specific application. The inlet temperature of this outlier turbine is more than 1100 degrees C, and it requires blade cooling. So also the blade cooling flows has to be managed in this case. It is relevant to say that in the previous cases, all the turbines were uncooled. Now, touching to future application, I'd like to mention the Carnot battery concept. As you know, Brighton cycles in different, let's say, forms are being studied for reversible direct and indirect operation in concepts such as Carnot battery. So to be used for energy storage solution at the industrial scale. In this case, it is possible to think of a supercritical CO2 cycle that could be used both as a heat pump during the charging phase as well as a direct cycle during the discharge phase. If we look at the layouts reported here, for instance, we are showing two different layouts for the discharge phase, where on the left is a simple cycle, simple supercritical cycle, and on the right we have a simple recuperative supercritical cycle. In this case, the let's say charging and discharging cycles, they interact in order to define the specification of turbo machinery, in particular if reversible turbo machinery wants to be developed. But if we look at the TS diagram of the two cycles, I mean one charging phase, the other discharging phase, and we look especially at the let's say the expander inlet condition, we see here that again, even for Carnot battery, we are talking about inlet conditions which are similar to the waste heat recovery case. The TAT, optimal TAT case is a little bit higher, 450 degrees C, during the let's say the charging phase, but they are quite similar to that case. Finally, I really, just to provide some food for thoughts, I'd like to touch on, let me say, the only at present commercial application of supercritical CO2. So supercritical or better to say transcritical CO2 cycles, are being used currently in CO2 refrigeration cycles, especially for large users such as supermarkets or malls. And in this case, we can see that, for instance, in the point 3 of this cycle, which is where the expansion occurs in the inverse cycle, there can be two cases commercially. One is just a simple expansion valve. Second one, having a nozzle for ejectors. Ejectors are currently used in CO2 refrigeration cycles. One third option, which could be a future market perspective, is to use an expander in the point 3. And I'd like just to remind here that there are a lot of challenges for modeling and for designing two-phase nozzles. In particular, the approach should tackle a number of phenomena which are not present in the normal single-phase flow, such as slip between the two phases, friction. The friction, let's say, loss becomes more complex due to the two phases. And then finally, also metastability, which is well known in the steam expansion, especially nuclear steam turbine field. Recently, we developed a work also based on original data provided by a refrigeration cycle manufacturer, and we were able to produce an empirical correlation able to predict the critical flow across two-phase nozzles with an accuracy which is average 5% relative error. In some cases can reach up to 15%. But in this case, I'd like to remember this is a good result, because when we talk about two-phase flow, uncertainty is still quite large. So to conclude with you, we can say the supercritical CO2 cycles for power production require high performance turbines. We have seen up to more than 700 degrees C and more than 200 bar. For waste heat recovery application or Carnot battery, we have seen that milder performance turbines are required, in this case maximum 450 degrees C and 200 bar. Nuclear applications are in the lower temperature range, below 300 degrees C, but of course safety there is a more relevant issue. For the outlier turbine, we have seen that fossil fuel oxy-combustion, such as in the alarm cycles, can require very demanding conditions, such as more than 1100 degrees C and 300 bar. If we look at the only supercritical CO2, let's say, or transcritical cycles commercial application, we can say that in refrigeration cycles, we have the need for reliable design tools for two-phase flow, especially in nozzles that can be used in ejectors or expanders. Ejectors are commercial, expanders are understudy. Finally, general conclusion, boundary conditions for supercritical CO2 turbines are much more application dependent than the compressor boundary condition. And this was, I think, the main message from my presentation.
Thank you very much, Alberto. Great presentation. Before we go to the next one, I will repeat how we treat questions in this webinar for people who came a bit later, who might have missed this information. So if you have questions for the speakers, you have two options. You either wait for the Q&A session, which will be held at the very end of the webinar, or if you want, you can already start writing them in the chat. It's always the best to say who the question concerns. And like that, the concerned person can already start replying in the chat. Well, all the questions will be answered. There are no worries at all about that. So while the next speaker is getting ready with his presentation, with his PowerPoint, I would like to introduce him. So the next one is Markus Sauerborn, who works as Senior Engineer Aerodynamics and Process Development in Atlas Copco Energas in Cologne in Germany. He has been working for this company since 1997. He has a degree in mechanical engineering from Technical University Darmstadt in Germany. For 12 years, he also acted as session chairman for the International Rotating Equipment Conferences, where he also contributed by his own research. And this year, he presented a paper on design and testing of an sCO2 compounder at the 5th sCO2 Conference for Energy Systems in Prague in the Czech Republic. So, Markus, thank you very much for being here. The floor is yours.
Yeah. So thank you, Jitka, for the kind introduction. So I try to share my screen now. Can you see that all? Okay, so
Yes, we can see it.
you can see it very good. So yeah, then good afternoon, ladies and gentlemen, and welcome to my presentation, which is about the CO2 expander design as part of a compounder working in a waste heat recovery cycle, as introduced before by Alberto, for 2 megawatt net output power. Okay, but first of all, I'm happy to introduce you to the Atlas Copco Group shortly. So Atlas Copco is a 150-year-old global and industrial company, which, let me say, is young at heart and with a highly innovative spirit. Our customers are active in a wide range of business in more than 180 countries. We have employees in 70 countries and employ approximately 49,000 people. 2022 revenues reached 13 billion euro and the operating margin was 21.4%. And here, this is our organization. We are a decentralized group with 4 business areas and 23 divisions. And as part of the compressor technique business area, the gas and process division develops, manufactures engineered to order turbo compressors, expansion turbines, and pumps for the gas and process industry, for example, including renewable energy, power generation, and CCUS applications, just as an example. Now let's come to our CO2 applications. Since we are dealing with high pressure, temperature, and power density, the mechanical design of the machine is a challenge. The picture on the left side is taken from a high pressure CO2 compressor, but is valid for an SCO2 expander as well. At a glance, you can find the critical components like volute, impeller guide vanes, shaft sealing, bearings, and gear set, which need to withstand extreme conditions in SCO2 applications. One of our latest references from 2013 is an 8-stage integrally geared CO2 compressor with a discharge pressure of 202 bars, replacing an old installation in a fertilizer plant. The operating data and some impressions from site, including the old piston machines, are shown on the right hand. In this regard, Atlas Copco Gas and Process benefits from many years of experience in SCO2 handling for the next phase of SCO2 turbo machinery development. Now, the machine design presented in this webinar is the expander stage of an integrally geared SCO2 compounder. The compounder was intended to be used in a simple recuperated Brayton cycle of our client's demo plant to recover 2 megawatt of exhaust heat from a gas engine driver. During the discussions with the client on the process, it became clear that for this application and the specified temperatures, a simple recuperated Brayton cycle, as shown in the TS diagram on the left and the related PFD on the right, was the best selection in terms of simplicity and machine design. The expander operates at the inlet conditions marked with a number 4 and the outlet marked with a number 5. You can see that in the TS diagram and also in the PFD. The expander inlet pressure is 220 bars, and the inlet temperature is 275 C. The outlet pressure is 82 bars. By the way, the compressor inlet conditions are close to the critical point, but slightly in the subcode region at 28 degrees C. This process design allows for an integrally geared machine design with a single turbine and a single compressor stage running back-to-back on the same pinion connected to the generator via bull gear and the coupling shaft as shown in the machine principle sketch in the middle. This is important for the machine feasibility, since due to the high pressure and power density on both the compressor and the expander impellers, excessive axial forces might occur and the gear set might be overloaded when not compensated in this way. Okay, on to the next. Yeah, here are two images of the compander. On the left, the expander stage mounted on the gearbox is shown, and on the right, the opposite side of the gearbox with the compressor and the seal gas connections. In the middle of the gearbox, the bull gear shaft, which will be connected to the generator via a coupling. Okay, here again, from a side view, both the expander and compressor stages mounted on the same pinion shaft. On the right, the cross-sectional view with gear set, which also drives the main oil pump, as you can see in the lower center part. Okay. Yeah, here on the next slide, an overview of the main aerodynamic parameters of the expander stage. The expander is a radial inflow type design. By the way, radial inflow expander was invented by Carl von Linde at our present location in the last century, just as a side note. And the impeller we have here is a shrouded design with an outer diameter of 150 millimeters and an inlet blade height of less than 10 millimeters, which is rotating at 38,000 RPM. The expander inlet conditions, as already mentioned, 220 bars, 275 C at a flow rate of approx 175 kilograms per hour, outlet pressure 82 bars, the aerodynamic output power approx 3.5 megawatts. So these figures demonstrate the extreme high power density in the expander stage and the challenges on the mechanical side to overcome during operation. The expander aero design was done with our in-house code, which is tested and calibrated from measurements of almost 200 expander stages in the past. As a gas property package, this RefProp was used. Okay, come to the next. One of the design challenges is the shaft sealing system, which you can see here in this slide. This consists of a patented arrangement of labyrinth elements as a primary seal next to the impeller backside. The primary seal gas is taken from the compressor high pressure discharge side, which also protects the subsequent driver seal from high temperatures. The CO2 vent line is located between the labyrinth elements connected to the process low pressure side. And as a buffer gas to the oil side, air is used, which is injected at low pressure between the two carbon ring elements. The CO2 air mixture between the dry phase seal and the first carbon ring element is vented to a safe location. Okay, some words about nozzle design or IGV. In the expander, high pressure casing guide vanes, also called the nozzles, accelerate the CO2 from velocity around 0 up to Mach number 0.8 at the impeller inlet. And for the order machine, a fixed nozzle ring was installed. But here in the next slide is shown if the process should require different flow rates. An adjustable nozzle ring design might be installed to control the flow over a wide range at stable efficiency values. And this is demonstrated in the diagram showing relative power as per the blue curve and the efficiency in green versus flow. Now some words about axial thrust, which is critical for sCO2 machine designs for the following reasons. In the sketch on the left, you can see the expander impeller with the impeller seal and the shaft seal, these two sealing elements. And now applying the balance of momentum over this surface S, as indicated by the red dotted line, though here the surface, it's an imaginary surface, by the way. The axial thrust is calculated by the equation as shown below. The first term on the right of this equation describes derives from the integration of the static pressure distribution, which is also the major fraction of the total thrust. The pressure distribution on the impeller back and the shroud side is shown on the right here. So in orange is the back side, in blue the shroud side. We can observe that there's a huge pressure difference between the impeller shroud and backside, and this might lead to excessive axial thrust depending on the position of the impeller seal and the shaft seal radius. Last, the second term in the equation on the right describes the thrust component from momentum change as the flow changes direction from the axial to the radial direction. Due to the high density of the CO2, also this component contributes a significant share of the total thrust when compared to other applications. In our case, however, the overall axial thrust compensation is reached by balancing expander and compressor impeller on the same pinion in back-to-back arrangement. So finally, startup and shutdown of the machine was a further challenge, as we have to bear in mind that the expander and the compressor are running on the same pinion in closed loop operation. This means in order to avoid overloading of the axial bearing, compressor and expander pressure have to be controlled over a relatively narrow band, especially during startup and shutdown procedure. The initial starting conditions of the loop were determined at around 38 bar, and the minimum starting temperature of 20 degrees C is required to avoid starting in the two-phase region. Now the startup procedure is shown in the TS diagram. The red dot here represents the compressor suction conditions. We will see that in the animation. In the following animation, the process loop operating cycle and its shift during startup sequence will now be shown marked in green like this. Now, after starting the machine, the compressor inlet temperature was increased up to 35 C by reducing the cooling power. This means above the critical temperature. Next, the heat load from the primary heat source is increased up to 100 degrees C expander inlet temperature, and now the loop and the expander operating conditions shift in the TS diagram like this. You see, we reduce the cooling, we increase the heat load, the loop shifts like this. The next step now is increasing this compressor suction pressure up to 60 bar by filling the loop. Subsequently, the heat load is increased to 160 C expander inlet temperature, and again we can observe the shift of the loop and the expander operating conditions like this. So we pressurize to 60 bar, increase the heat load, and the loop shifts like this. This is now repeated to a 90 bar compressor inlet pressure and 160 C heat load, and now the shift is like this. Finally, we increase to the cooling to 28 C and depressurize to 80 bar, approaching the saturation line and compressor inlet, followed by increasing the heat load again to the nominal expander operating point at 75 C and 220 bars at the inlet. So increase the cooling, 28 C now at compressor inlet, depressurize to 80 bars, increase the heat load. Now we have the final operating step and nominal operating conditions. So thus the these conditions are reached by following the red dotted path in the TS diagram around the dome like this, starting from gaseous to supercritical and finally to the liquid state at compressor inlet by avoiding two-phase region. Okay, let's come to a summary and conclusion. In this webinar, the design of an sCO2 expander stage as part of an integrally geared compander for 2 MW output power was presented. Atlas Copco's long in-house experience and enabled us for the development of an sCO2 expander as part of a compander operating in a waste heat recovery cycle, as mentioned. We were awarded the first order for a customer in 2018. And challenges for the machine design and the solutions in regards to aerodynamics, shaft sealing, mechanics, axial thrust, and process controls were presented. Finally, a first commercial market machine in the market machine for sCO2 applications was delivered. So that was my presentation. Thank you very much for your attention.
Thank you very much, Markus, for your presentation. It was very informative, interesting.
Thank you.
So we are ready for the third speaker. So while he's getting ready, I would like to introduce him. So the next speaker is Stefan Glos, who studied mechanical engineering at Ruhr University Bochum in Germany, where he got his doctorate in the field of experimental thermodynamics. He works for Siemens Energy in Mülheim, where he holds various positions in customer order engineering and R&D. Stefan is an expert in the thermal design of turbines for different working media like steam or CO2. Since 2015, he's responsible for the development of innovative product and system concepts within the steam turbine business area of Siemens Energy. So Stefan, the floor is yours. You are muted.
Sorry for that.
Never mind.
So now you can hear me and you can see my screen, right?
Yes.
So then
Yeah.
thank you, Jitka, for the introduction, and good afternoon from my side. Yeah, in my presentation, I will emphasize the benefits and the design challenges of especially axial sCO2 turbines. And with that title, I will directly jump in my presentation and showing first an overview of the agenda. I will start with some basic considerations. So recap a little bit, what are the benefits of supercritical carbon dioxide as a working medium? And then from the basic working principles, I will derive some main requirements and challenges on the design of sCO2 turbines. Then I will look shortly on the application range, especially of axial sCO2 turbines. In the last presentation, we have heard about a radial one. And then in the main part of my presentation, I will show some insights of a turbine development, a 2 megawatt demo turbine, which we have designed within the Cool Heat project, which was already mentioned as well by Alberto, I think. And I will go there a little bit into details of some mechanical aspects, but as well of the optimization of the inlet volute. I will very briefly say something about the impact of the pressure losses and the windage heating effect in labyrinth seals. And then finally, I have one slide of the dry gas seal integration, and will close my presentation with a short summary. So why shall we use sCO2 as a working medium? What are the potential benefits? And I guess most of you will have the 4 bullet points, which you can see here on the slides, in mind. So we all read and know about the higher cycle efficiency of sCO2 cycles, and the smaller components, especially the smaller turbines, and then the related footprint. Regarding the efficiency, I would like to emphasize that this is for sure not valid in each and every use case. There is an echo. Maybe someone has to mute his phone.
Stefan, now
Stefan, you're muted.
Okay.
Yes.
Once
Thanks.
again. So I stopped at the higher efficiency, and I said that this is really depending on the use case and depends on the heat source, on the power output, we think, and on the heat sink temperature, especially. The higher fluid density leads to smaller turbines and to a smaller footprint. On the left-hand side here, on the lower end, you see a comparison we did once within the Cabo Solar project, where we have investigated a waste heat recovery use case 36 megawatt and compared a steam turbine you see on the left-hand side and an sCO2 turbine on the right-hand side. And you see that the main driver for a lower footprint and smaller machines comes from the cold end. Means at steam turbines we are expanding at the cold end into the vacuum, and there the volumetric flow is orders of magnitudes larger than in a high pressure sCO2 cycle. At the inlet of the turbine, the volumetric flows are quite similar. So there we have, let's say, a similar cross sections, so that at the end the main advantage comes from the cold end, or is driven by the cold end, let's say. Looking on the working principles of an sCO2 cycle, we see here just a simple example of a recuperated cycle, in this case for a waste heat recovery application, and the process here on the left-hand side in the TS diagram. And from that, we can already derive some basic requirements and challenges. So the first one is for sure the high pressure level in sCO2 cycles, or at the inlet of the turbine, we are speaking about pressure levels of 250 to 300 bar roughly. So therefore you need a mechanical design of the machine which is really suitable for that. When we started to look into that technology, we realized that our barrel type high pressure steam turbines, which are used especially for high pressures in coal-fired power plants, are very suitable for such an expansion. And the second challenge, I think, comes from the fact that in sCO2 cycles we always have a back pressure turbine. Means the lowest pressure level in the system is in the area of 60 to 90 bars. And that implies specific operations on specific requirements on the operational concept. Means how to start up the system. What about low load conditions or no load conditions? Have we think about windage? And furthermore, the sealing technology, which was already mentioned in the first Slido. Then we have a comparable low expansion line, means we have quite low enthalpy drop, but significant high pressure drop. And from that you can conclude, or from the low enthalpy drop, you can conclude that you need a high mass flow circulating in the system. And on the other hand, you will get quite few stages, at least significant less than in a steam turbine, but these stages then have to deal with that large pressure drop. So that leads then to high or to robust airfoils, and furthermore, the internal leakages become more important, let's say, and you have to take care about that as well. And last but not least, we have already heard that the high fluid density. There you have to design, or you have to design the aerodynamics of the inlet and the outlet quite accurate, and have to take care there that you avoid local accelerations of the flow, so that you keep the secondary losses in an acceptable range. And furthermore, you have to take care about the rotor mechanics and the rotor dynamics. Looking on the application range of the sCO2 cycles, and here you see a chart which we have shown already a few times. You see the process temperature over the power output, and here you see very roughly the areas of applications, and most of these applications were already mentioned by Alberto in his first presentation. So one is the waste heat recovery application. In two, we have solar thermal or direct fired applications. Then in three, that's a special use case which we are following since a few years, which is a direct geothermal use case. Then number 4 is the oxy-fuel combustion, and 5 the area of heat pumps or pumped heat energy storage systems. And below that diagram, you see where we think that axial turbines can be used. So we think that starting roughly in an area of 10 megawatts, we think that a reasonable axial design can be built. For the Cool Heat project, which I will show starting from the next slides, we were able to realize a very small axial turbine with a shaft diameter of roughly 160 millimeters and running at 10,000 RPM. And if you scale that design up, you will reach somewhere between 30 and 50 megawatt the net frequency, so that you don't need a gearbox anymore, and then you have a roughly a diameter of 400 millimeters. So, as already mentioned, within this the European-funded Cool Heat project, we have designed a high-pressure barrel-type turbine for sCO2. The goal is the realization and the validation of this demo plant. Unfortunately, this project is still on hold, but we are working on further progress. But we had always in mind to have a design which is then scalable to larger power output, and we did that exercise, which is roughly shown here on the lower end of this slide. So for 2 megawatt, we get a rotor length of roughly 1.7 meter, and if we scale that up to 50 megawatt, for instance, we have only a shaft length of 3.4 meters. But before we started with a detailed design of this concept, we started in a design study. So we had 3 principal arrangements of a turbine, or 3 different turbine concept. 2 barrel type turbines here, number 1 and number 3, and 1 joint type turbine with a horizontal split. And we looked not only on aspects like aerodynamic, rotor dynamics, and mechanics, but also on the cost, assembly, manufacturing, procurement, and what was very important for us, I've just mentioned it, was the scalability then to larger outputs. At the end, and I will not show that here in every detail, we choose the design concept number 1, which is a barrel type turbine. And I will go a little bit into detail for one aspect which we have checked and which was a significant drawback for this joint type turbine on the right hand side, which was the gas tightness. Means due to the high pressure and due to the fact that we had to implement here the dry gas seal in the outer casing, yeah, the gas tightness was really hard to realize, whereas in the left concept in this barrel type machine, this was really no issue. Here you see it once again. With another drawing, and this was really one of the largest drawbacks of this joint type turbine. And another interesting fact was when we looked on the inflow of the machines, and on the left hand side you see the inflow of this barrel type machine, and here we could realize and finally optimize volute geometry so that we got a very homogeneous flow leading to very low pressure losses. And for this joint type turbine, we had let's say, more or less conventional inlet geometry, leading to locally very high flow velocities and as well a large variation. And this, as a result, we got very or higher pressure losses. But this was not the only drawback for the right concept here, but resulting from that, from this large pressure variation, we got as well quite a large resulting force on the rotor, whereas on this barrel type machine here, the resulting force was quite low, and this was as well another advantage for that concept. Now I have one slide. I thought it was quite interesting, but on the other hand, maybe some of you will already know that. But this was something we have already investigated when we started with that investigation. So we know all that the performance of sCO2 cycles is quite sensitive to pressure losses. And if you are designing such a machine, and you know, we are coming from the steam business, and in the first approach we assumed, let's say, same speeds for the inlet flow as we are usually doing for steam turbines. We realized that we got very high losses at the inlet of the machine, so that we concluded that the thermoeconomic optimization of the turbine, but I think as well of the cycle, will lead to larger flow diameters, at least at the high pressure side of such a system. And the second effect which we have investigated very briefly is the flow through a leakage seal through the labyrinth seal. I'm sorry. So labyrinth seals are used for the internal seals, such as on a thrust piston, but also on the shaft ends in steam turbines. That is especially on the thrust equilibrium piston. Here we are using these kind of seals, and here you have to have in mind that the circumferential wall shear at the rotating shaft will heat up the fluid, and with CO2, the resulting temperature increase of the leakage flow is significantly higher than in steam or in air applications. So this has to be considered in the mechanical design of the rotor and of the casing, and this is especially important for high temperature applications. Regarding the dry gas seal implementation, I think I can keep it here short, because the statements are quite similar to the last presentation. Let's say maybe you can have a look on this right hand picture here. This was the sCO2 machine then integrated in the whole powertrain. So this small gray machine here is the sCO2 turbine, which is then connected over with the gearbox in green to the generator in red, and everything here is mounted on a base frame. Regarding the dry gas seal, maybe one further comment. What we have realized, especially if you think of upscaling such a machine, you really have to have in mind that there are certain limits of these dry gas seals with respect to size or with respect to allowable temperature, which has to be considered as well. So that I'm now at the end of my presentation, just a short summary. sCO2 turbines provide certain benefit in terms of performance and compactness. The design challenges, which are mainly based on these fluid-specific properties, must be considered. But we think that our very proven high pressure turbine concept is very suitable for that. And for us, we think that the main challenge is still, let's say, the remaining realization of such systems. So with that, I would say thank you, and looking forward to your questions later on in the Q&A session.
Thank you very much, Stefan. Very interesting. I'm not the only one, I see. Get lots of applause. Very nice slides. So while the last speaker, but totally not at least, is getting ready, I have the pleasure to introduce him. So the fourth speaker is Andrea Paggini, who works currently as the principal engineer for steam turbines and axial expanders at Baker Hughes Nuovo Pignone. In this company, he has more than 23 years of experience in different roles, both technical and managerial, within the steam turbine engineering team. In the last years, he acts as a technical coordinator for various R&D programs dedicated to steam turbines and to axial expanders for new emerging applications, mainly sCO2 and liquid or compressed air energy storage. This is it from me. Andrea, the floor is yours.
Thank you, Jitka. Good afternoon, everyone. Oh, sorry. Just 1 second. Can you see my screen? Yeah, okay. So in this presentation, yes, I will summarize the Baker Hughes experience gathered with unfired sCO2 expanders, identifying the main design challenges, either generally applicable or, let's say, peculiar of some specific application or expanded architecture. So with that said, this slide, this slide reports, summarizes, let's say, the main projects that we have worked on so far for axial expanders. These are all projects developed within the framework of Horizon 2020. You can see either applications with pure CO2 for fully supercritical cycle, or CO2-based mixtures for transcritical cycles. You can see power levels ranging from a couple of megawatt desalination to 130 megawatt Scarabeus. Desalination would actually be a power size more, let's say, more suitable, ideal for radial machine, I would say. But considering that radial machines are intrinsically more limited in terms of power deliverable, and thinking to the possible power scale up at the commercial scales of this plant, we have deemed crucial to increase the technology readiness level of axial machines. So you can see here the thermodynamic conditions for these projects, which are, let's say, pretty much representative of a big part of the sCO2 galaxy, let's say. So inlet condition above 200 bar up to 250 bar, and inlet temperature from more than 500 degrees to even 700 degrees C. So these conditions are not far away by the normal values encountered in ultra supercritical steam technology. Nevertheless, sCO2 expanders have some peculiarities requiring, let's say, special care in the design, and I will try to summarize something. So in this slide, instead, it's reported the Baker-Hughes experience gathered on radial expanders. So also in this case, the Cool Heat project is part of the Horizon 2020 program. Actually, radial architecture was studied also in the conceptual phase of the FLEX project, since, let's say, initially, let's say that there were more than 20 cycles on the table, and before selecting the final cycle layout, both radial and axial technology, let's say, were studied in the conceptual phase. So axial technology was chosen only after the definition of the cycle. So a few, let's say, a few features relevant to the Cool Heat project. Also, in this case, it's an integrally geared compressor expander, so a machine pretty similar to the one explained by the colleagues from Atlas Copco. So you have also in this case outward stages for the compression and inward, let's say, impeller for the expansion. You have in both cases, the stages are arranged in back-to-back configuration for a better management of the axial thrust. What to say? Again, the integrally geared design allows to decouple the rotating speed between the expander and the compression. So, in principle, it's you can select the optimal rotating speed for each machine. This kind of machine are pretty much also due to the relatively small size, are pretty much let's say sensitive to non-scalable let's say geometrical parameters, roughness, and also to a certain extent also clearances. So just for roughness, it's worth mentioning that with a few 5 microns roughness, the efficiency penalty is 2.5%. So it's something which is huge. And so as far as concerned clearances, even if a shrouded design for the impeller, for the wheel, is more critical and challenging from the standpoint of the mechanical design, it allows to have a better control of the clearances resulting in 3.5% of efficiency gain with respect to the open wheel. So just entering some, let's say, technical details of the challenges applicable in general to axial expanders. So sCO2 expanders are known to be compact machine, and this is true. Nevertheless, there is a sort of downside that arises as a downside of that advantage. You can see here in that graph a comparison between the inertia that you have for 2 expanders of sCO2, Flex and Scarabeus, and the inertia of real references of industrial steam turbines for power generation. So I think that no comment is necessary. So you can immediately appreciate the huge power density which characterizes these machines. What does it mean, such a large power density when designing the machine? Which are the challenges? One immediate criticality is that in case of loss of load, so essentially an event of a generator breaker opening, for example, or even in the case, which is even worse if in case it's applicable, in case of loss of load and inertia, so a coupling failure scenario, the overshoot speed reached by the rotor is well above the typical values encountered in steam turbine training as a result of the large power density. And so it established, let's say, very challenging requirements for the responsiveness of the trip system and for the overshoot capability of the rotor. There are also, let's say, further design challenges which are indirectly or broadly correlated to the huge power density. I would mention rotor dynamic and flow path mechanical design. So for rotor dynamic, it's so these kind of machines are very sensitive to the destabilizing forces coming by the flow path design. So the rotor dynamic stability is very much affected by these destabilizing forces. So I'm referring to the Alford effect and to the interstage cross-coupled stiffnesses, which are typically the major sources of destabilizing actions. So it's extremely important to have accurate and validated models in order to have a reliable prediction of the rotor dynamic behavior of this machine. One more point is that even from a purely static sizing of the airfoils, the result is that in reason of the high density fluid and of the, let's say, large forces exerted on the airfoils, sCO2 expanders are typically, let's say, characterized by low aspect ratio steam path. Aspect ratio is the height to chord ratio of the blades, which in principle is an effect detrimental to efficiency. Nonetheless, for the flow path of the Scarabeus, the machine 130 megawatt that we have seen earlier, we have it has been achieved a 93% flow path efficiency, which is really a remarkable result, considering also these kind of challenges. So we could summarize saying that, as far as concerned the problematics broadly or directly correlated to the power density, blended CO2 expanders are essentially critical as pure CO2 expanders. There are no special peculiarities. One more point I wish to talk about, even if it has been touched in the other presentation, is drag seals. Drag seals are unavoidable for sCO2 expanders. The reason is that with the minimum pressure of the cycle, which is above 80 bar typically, you cannot afford, let's say, for the shaft end seals of the machine, you cannot have a labyrinth design of the seals. It would result in a completely unaffordable leakage. And when I say unaffordable, it could mean or a huge leakage to the atmosphere, or in case the leakage is recompressed, which is a viable option, it would result in a huge recompression work, very much penalizing and detrimental to the cycle efficiency. So drag seals are mandatory for drag seal expanders. The problem is that the current drag seal technology is currently limited in temperature. So we are saying the maximum temperature is around 250 degrees C. Drag seal suppliers are working a lot to push up the temperature limitations, but as a matter of fact, at least in the short, medium terms, no viable option other than drag seal cooling exists. And so it should be somehow intuitive that finding an optimal compromise between conflicting requirements like cooling effectiveness, cooling flow minimization, limitation of the thermal stresses induced in the hot components is a tricky task. Probably this was, let's say, in the slide question, the thermal management challenge that was answered by some of the people. In this sense, it's definitely a correct answer. Stefan also mentioned that dry gas sealing are limited in size. So if you think to scale up a CO2 expander beyond certain limits, so as a matter of fact, there is currently a torque transmission capability. So you cannot transmit the torques that typically you have in steam turbine trains. What I've just said applies to the case of pure CO2. Which are the peculiarities of the CO2 blended expanders? So if you have pure CO2, in principle, you might even afford a minimal release, a minimal leakage to the atmospheres, just a few grams per second, since we are speaking of these numbers. But if you have blended CO2, since all the possible dopants added to the CO2 in order to have the required shift of the critical properties are gases that should not be vented. So typically sulfur dioxide, titanium tetrachloride, hexafluorobenzene. So you need to have a buffer flow of pure CO2 in order to avoid such a leakage. And if you wish to minimize the amount of pure CO2 buffer flow, since it cannot be avoided, it enters the process loop, contributing to a certain dilution of the working mixtures. All these requirements, let's say, force a dry gas seal peculiar design in a component which has already its own criticalities. So from that standpoint, from dry gas seal standpoint, we could say that blended CO2 expanders are a bit more critical than expanders for pure CO2. The last topic I wish to talk about is materials. So it's well known that martensitic stainless steel material, 12% chromium, which are materials extensively used in steam turbines up to temperatures well above 600 degrees C, are prone to oxidation and carburization in a high temperature CO2 environment. So this is, let's say, there is not an exact threshold above which the usage of martensitic steel in CO2 is forbidden, but there is a consensus that the switch to other materials should take place at temperature lower than in steam. So which are, let's say, the design alternatives at disposal for when designing these machines? Number one is to switch to other materials. I picked here just one graph from the enormous amount of literature available, where you see that austenitic steel behaves better in terms of material compatibility with CO2. Nickel-based alloy is even better. Option two might be to maintain, let's say, martensitic steel for certain components, providing a protection layer by means of coatings or cladding. Option three might be a dedicated cooling of some specific components, or even, let's say, all the three options combined together. So what is important to say is that so far, to Baker Hughes, let's say, actually there is no technical, let's say, better choice to manage material, since it's not only a technical stuff, but is also an economic stuff, since nickel-based alloys have costs which are 5 to 10 times the cost of conventional steel. So economic considerations play an important role. It's important. So the best strategy the strategy that we are working on is to maintain martensitic steel for the external casing, which is the most massive component, having geometries typically suitable to be protected by means of coatings or cladding, and switch to different material when requested by the application for the other components, which are other components in contact with the process fluid, so valves, blades, shaft, inner casings. So this is, to us, the most promising strategy. What about the case of CO2-based mixtures? So in this case, based on the results gathered achieved on the desalination project, following compatibility tests carried out at the University of Brescia, let's say the measure outcome of this test is that the presence of whichever dopant, titanium tetrachloride, hexafluorobenzene, or sulfur dioxide, as a matter of fact, restricts a lot the list of possible materials for this application. You can have that one material, one alloy is behaving extremely well with a certain dopant, experiencing minimal interaction with the fluid after 2000 hours, which is the maximum duration of the exposure tests gathered so far. And the same alloy with another dopant is, let's say, the least performing, totally inadequate for the application, and you discover it just after a few hundred hours of exposure. So for blended CO2 expanders, materials are, let's say, an important and a challenge very much important. So a few remarks as a conclusion. Apart from materials, the technical criticalities of expanders for carbon dioxide mixtures are comparable to the case of pure CO2. Addressing materials and manufacturing processes more in details is the most crucial aspect, primarily for blended CO2 application, for blended CO2 expanders, to fully exploit the advantages claimed by the sCO2 technology. Despite the technical challenges highlighted, the turbomachinery design is able to achieve the technical objectives addressed by sCO2 technology in terms of efficiency, compactness, and operability requirements. Last comment, the development of a demonstration plant is really a key enabler for the success of the technology. Thank you, everybody, for your attention.
Thank you very much, Andrea, for your great presentation. So this is it. We have heard all the 4 speakers with 4 great presentations. And before we get to the Q&A session that I was talking about before, we still have one Slido question. So let me share my screen. So we would like to know if, in your opinion, there are any remaining challenges for the sCO2 expanders that need to be addressed. And if you think that they are, which ones would they be? So again, I will ask you to use 1 to maximum 3 words. We already have quite a lot of answers. So I'll ask my colleagues to step in and to debrief on what we see.
If I can comment.
Yes, please.
No, I think I agree with essentially all the things that have been written. Probably the only difference is that some challenges, at least let's say based on analysis, are addressed. So for sure, for example, dry gas seal on the paper should work. So the cooling system studied should work. This is why I ended my presentation saying that a demonstration planting is in any case fundamental as a validation. But there are other, let's say, topics which even from an analytic standpoint probably are a bit behind, requires more development. And to me, I probably agree with the materials. With pure CO2, there is a huge amount of literature, but the long-term durability to me is still an open point. For blended CO2 application, as I concluded my presentation, it's really a huge, a hot topic actually. I don't know whether my colleagues wanna say something more.
I have a comment on this because actually when I was seeing them popping up, it's a comment that also brings a question to the industrial, let's say, representatives here. I mean, if we see here validation results. Okay, now validation results is big. Okay, and I think I mean includes many other challenges that are related here. So the question is, when you design a steam turbine, okay, let's say you are 99% confident that the design will be reflected in your system, in your turbine, okay? Now, according to this scale, 99% in the steam turbine design, you know, loss correlations are great, performance correlation works. What's your level of confidence with CO2 expanders?
It's a question for who? For all?
All of you that manufacture turbines.
I would say, I don't know, 70, 80%. So based on analytic result, we can be confident, but for sure validation is really what is still missing. What is still missing, as a matter of fact. This is my opinion.
Yes, I would agree basically. So as mentioned in my presentation, we have a huge experience in expander design, but this is for sure a special one with high inlet temperature, and therefore we would like to see the real performance in operation, as we do not have any possibility to test the machine and see the real high temperature operation. So would be the only outstanding point here for us to be sure.
Stefan, would you also like to comment to this question?
Yeah. Now, for me, validation has several aspects, right? You can first of all, you can validate your performance models, all your prediction and pressure loss and all that stuff. But there, I would say we have a very good theoretical basis. I would be quite confident. Then there is the aspect of, let's say, long-term validation. If we think about material, how does the material behaves after a certain period of operation? And then we have the field where I think as well that validation is very important is all these system topics. How does the whole system behaves in specific operational modes like startup, shutdown, and all that stuff. I think there is a large field where we can learn of the system behavior.
Alberto, your question is answered.
Yes. I think there is a common understanding that if I would have written a remaining challenge, I think we need some activation energy for the industry to go from the prototypes to the 100 megawatt, because that's what these machines are for. So that's my feeling. I mean, also the industries is quite clear. They're looking for, if possible, axial machines. Siemens clearly axial machines. So and there is a gap there, which is mainly, let's say, bankability gap, because there is a challenge that is difficult for someone to tackle, which is the technical risk of building the first of its kind. But still, okay, I think we are on the right path.
Thank you. Andrea, there is a question from Dinesh for you in the chat.
Okay. I was writing in the chat, but perhaps it's easier to in speech. So I focused my presentation only on, let's say, unfired expander since 15 minutes to speak about the technical challenges of an expander for the Allen cycle would be, let's say, very probably ridiculous. So in the end, the machine for the Allen cycle is much more challenging, and we are developing such a product in a research and development program which is much larger. In any case, the point you raised, Dinesh, is very much, let's say, it is true. So the effect of also these impurities is something that can have impact on material selection and durability, and so definitely let's say the state of the art is not as far as concerned materials is not a mature technology. Okay, so a lot of further testing are required to make the assessment in this regard. So it's something which is definitely in progress, not yet let's say finalized, this topic.
Thank you. Dinesh, is your question answered?
Yes. Thanks for the clarification.
Okay, excellent. Are there any other questions?
If I can ask one more question.
Sure.
Can anyone comment also on the erosion observed or reported from the turbine blades from Sandia test rig, and how significant is that, and how that scales for the when we are scaling up the turbines, and what's that understanding?
And who is this question for?
It's an open question, I guess. Yeah.
Okay.
Yeah, you are referring to certain results from this step facility, or?
It's in the Sandia a small scale rig. There was a reported erosion of the turbine blades, and so just wondering whether any lessons learned or any points to highlight where we are currently.
Yeah, to be honest, I can't comment to that. I would. I don't know these results, to be honest, and I would, if you are saying about erosion of blades, I would guess it's caused by some hard particles or something like this from the system, which is, I would guess, probably maybe not specific to CO2. But
may I add something?
Yeah.
Though it was exactly erosion, it was a concern. But for example, within the Flex project, let's say the topic has been studied in detail. For sure, no demonstration expander has been done. But in the Flex project, let's say erosion test in test loop. I do not remember the velocities of the fluid, but probably up to 100 meters per second were done. And I think that the report should be public. I think, in any case, to my mind, the effect of the fluid velocity was not that dramatic as, let's say, as expected. Probably, this is my, let's say, this is what I remind from these reports, since the tests were carried out by other partners within the Flex program. But in any case, it was a topic addressed.
Okay, thank you both. Yeah, for clarifying that.
So are there any other questions? If this is not the case for the moment, you can always come back to us later on. You have our contact details. Once you receive presentations, you will also have contact details for all the 4 speakers, so you can address them with any remaining questions that may cross your mind later on. So if this is it from your side, then let me thank you very much for being here with us. We really appreciate your presence and your engagement in Slidos and in Q&A session. This webinar series will continue. It's conceived as a quarterly, so we will organize another session. And already today we can unveil that the next topic will be balance of plant. So you will be all informed about it. You will receive an invitation and a few reminders. As I said before, you will definitely receive the proceedings from this session. So all the presentations, a few more slides that you have seen, because our speakers were not able to cover all the topics that they wanted. And you will also receive the link to the recording. I see that Marco raised his hand.
No, it was just a mistake. I wanted to clap my hands, and the button is right beside it.
Okay, but thank you very much anyway. So with this, I also thank to all my colleagues that were on the stage, and everybody else who supports this webinar series. Thanks again. Have a nice afternoon, and see you soon. Goodbye.
Bye bye.
Thank
Thank
you.
you.
Bye-bye. Bye.
Bye.